Okay, it's time for the Chapter 7 Homework 1 review. This is our assignment that covers most of everything in Chapter 7. There's going to be one topic, maybe one or two topics that'll still be in next week's assignment as well. The average on this one was 8.97 out of 12. That's a little bit lower than our typical homework average, which is what we usually see for the assignment that's due right after the exam. So definitely take some time to make sure we address some of the issues that were present on this one. Obviously the exam was most people's priority this week, and we probably fell a little bit behind on the new material, but definitely don't want that to linger on too long. So make sure you look through the homework questions that you just did. Come find me for any help that you need on trying to figure some of them out, and try to stay caught up as much as possible as we go into the last few weeks of the course. All right, so we'll jump right into it. The first few of these are requests from students, so I will cover those first. And then from there, I'm going to go through several that represent topics that either we didn't do very well on the questions overall, or a couple topics that I just want to make sure that I cover in a little bit more detail than I did in class. All right. So the first of these, a lot of these questions that we deal with are conceptual, and there's a couple here anyway that we'll deal with. Delta E, delta H, and some of the simple relationships between them. So this one here is a little bit more quantitative in nature, and we have a reaction shown here, already given to us balanced. We're running a bomb calorimeter, so the delta E was found to be minus 742.7. Calculate delta H for the reaction at this temperature. Now this is a type of calculation that I didn't actually do in class, so it's one that you would have had to sort of figure out on your own really the best way to approach this. We did give you a hint here that's going to be important, which is that P delta V is equal to delta N RT. And now some of these topics, and this is one of them that I'll be fully transparent on, some of these topics are going to make more sense after we've covered Chapter 8 and to some extent Chapter 9 as well. So Chapter 7, 8, and 9 are sort of intrinsically linked to each other. It's hard to sometimes get all the details from one without knowing some of the background from the others. So I think by the time the third exam comes around in the final, we will have covered all three of those chapters, and a lot of these topics will begin to crystallize for us as we have all that information. So this is one where this hint that we give you really relates to what's called the ideal gas law, something we're not going to cover until Chapter 8, but we have enough information to solve this. So we have delta E, we're trying to find delta H. So remember that delta H is equal to delta E plus P delta V. So that's the relationship between the two. That we should know. We covered that in class. And then what we're looking for here is we already have delta E, so we just need to find this P delta V term. Now we don't have anything about pressure and volume in this problem, but what we have the hint is that we can rewrite this as delta E plus delta nRT. Temperature is constant, 298 Kelvin. And so if we want, we can write this as delta E plus RT delta N. So the only thing that's really changing here is potentially number of moles. So it's constant temperature. R is a constant. We haven't covered this one yet, but that's one of the constants on our periodic table. There's two different values of it. We're going to use both of them to some extent, and especially in the next chapter we'll use it a lot. So this is the relationship we want to use, delta E plus RT delta N. So the only thing that we're not sure about here is what is delta N. So delta N is equal to change in the number of moles of gas. So whenever we have this relationship involving delta N, we're talking about gas specifically here, not all moles, just gases. Because remember that when we have a change in volume or any sort of expansion work as part of the process, which is what P delta V refers to, that expansion work is typically involving gas phase reactants and products. When we have solids and liquids, their volumes and pressures don't really contribute or change very much. So we're really thinking about gases here. So delta N is change the number of moles of gas between reactant and product side. All right, so on the reactant side, if we look at the balance equation, we have 3/2 moles of gas, that's the O2. And then on the product side, we have 1 mole of N2 plus 1 mole of CO2 which is 2 moles of gas. So then the change in the number of moles of gas, delta N, sometimes we put a little g here to remind ourselves that it's gas, is going to be products minus reactants, so it's going to be 2 moles minus 1.5 or 3/2 moles, which is plus 0.5 moles. Alright, so the delta N, the change in the number of moles of gas, is plus 0.5 moles. That means there's 0.5 more moles of gas on the product side as reaction side. And whenever the number of moles of gas is changing, we expect then there to be a non-trivial P delta V term. Okay? So finally, we can put the numbers in. Delta H is going to be our given delta E, which is minus 742.7. Then we have R, which is the universal gas constant. So this is in kilojoules. And we need RT delta N. So if we go to the periodic table, universal gas constant R is down here. And there's 2 values, as I said. The one that we want to use, typically when we're dealing with delta H and delta E, and is this one here, 8.314. Now that's joules per mole Kelvin. So our universal gas constant R that we need to use for this number here, R is equal to 8.314 joules per mole Kelvin. We want this in kilojoules so that we can add it to delta H. So that's going to be 0.0, let's see, make sure I get this right. Enough zeros in there. 0.008314 kilojoules per mole Kelvin. So we can do the conversion before or after putting the numbers in. We should make sure that before we add these 2 terms together, delta E plus P delta V or delta E plus RT delta N, as we've rearranged it to, before we add those, they have to be in the same unit. Okay, so we're going to put 0.008314 kilojoules per mole Kelvin. Temperature is given to us at 298 K. So in this case, temperature has to be in Kelvin anytime we're doing absolute temperature. And then delta N, as we said, was 0.5 mole positive. So when we add these together, 742.7, we get minus 741.5. We have it as kilojoules per mole. Kilojoules is fine, as the answer choices say. So the answer choice would be C. So delta E plus P delta V. So as you can see, they're not very different from each other in this case. But because there is a non-zero delta N, this is the key term here that tells us whether or not delta H and delta E are the same. Because that is non-zero, it's 0.5 in this case, not a huge number, there's going to be some difference between delta H and delta E. And as you can see, it's on the order of just 1 kilojoule in this case, so not a huge amount in a relative sense. Alright, so that's how we approach that one. We didn't really do any calculations with that concept, but we did talk about the difference between delta H and delta E. And if nothing else, this problem demonstrates to us that delta H and delta E are usually very similar as something else that we sort of highlighted in class. Alright, so this question here is on a similar concept. It wants to know which of the following describes the signs of Q and W for the following exothermic process at a constant pressure. So if we're at a constant pressure, remember that the definition of delta H is that it's just equal to the heat at constant pressure. Alright? And the key word here is that this is an exothermic process. So anytime we're exothermic, that tells us that delta H is negative, less than 0, which means that the heat must also be less than 0. So if we're at constant pressure, delta H and Q are the same. Delta H is less than 0. That means Q has to be less than 0. So Q has to be negative. So the only answer choices that we can even consider are ones where Q is negative. I think that's the more straightforward of the two to deal with between Q and W in this case. So Q is positive, so we can get rid of choice B. Q and both are both positive. It's not 0. So now we're just left with 2 answer choices. We know that Q has to be less than 0 because it's an exothermic process. Now how do we deal with W in this case? This is the one that's more difficult. So we said that delta H is equal to delta E plus P delta V. We had that relationship. We don't really anything about that here because we're not asking about delta E specifically, but we know that the work term, which is what we're also asking for, is equal to minus P delta V, okay? And so what we need to figure out then, this is at a constant pressure, so this is a constant, but is delta V going to be positive or negative? All right. And again, that's where we look at the reactants and products and figure out where we have gases and where we don't have gases. So if we have on the reactant side, we have 1 mole of gas, H2O gas. On the product side, we have 0 moles of gas. If the number of moles of gas is decreasing, that means delta V must be negative. Okay? So anytime, this again will make more sense when we go through chapter 8, but gases take up more volume than liquids and solids. So we have delta V in this case will be negative because we have more gas on the reactant side than on the product side. So the amount of gas is decreasing during this process. We're going from gas to liquid, so we're losing, the amount, the moles of gas is decreasing. And so anytime there's more gas on the reactant side, the delta V term is going to be negative. Work is equal to minus P delta V, which means that it would be equal, which would mean that the work has to be positive in this case. Okay, because there's a negative sign out front, delta V is negative, a negative times a negative is a positive. So the correct answer choice then is C, where Q is negative, that we determined by the fact that it's isothermic. W has to be positive because the system is compressing. We're going from a gas to a liquid, that means the volume is decreasing. Anytime the volume decreases, the work is positive because of this minus P delta V equation. All right, so again, that just requires us to think a little bit about the equations, but more in a conceptual sense, and how we think about heat, work, and delta H and all those things in their relationships. All right, this problem here also deals with mostly just the sign of delta H and delta E and things like that. So the dissolution of barium hydroxide in water is an exothermic process. So again, that means delta H is negative. Which of the following statements is correct? So the first few of these statements, A, B, C, they ask us to really compare the enthalpy of the reactants and products. So if we're talking about dissolution, remember dissolution means dissolving something. We're taking barium hydroxide, which is BaOH2. We don't really need the formula for this one, but this is our reactant. And when we're doing a dissolution process, we're starting with this as a solid. We're adding it to water. So as I said, we sometimes just put water above the reaction here. It's not really a reactant, but it's participating in this process. And then the final product is going to be aqueous barium hydroxide. Okay, so again, it's not really a reaction per se. It's just a phase change. We're going from solid to aqueous. So that means our reactants in this case are going to be the solid barium hydroxide in water, and our product is going to be the solution, which is the aqueous barium hydroxide. So delta H is going to be negative in this case because it's exothermic. That was the key word we looked for in the problem. And remember that delta H is equal to the enthalpy of products minus reactants. So when we're talking about chemical reactions or dissolution processes like this, remember, a delta means final minus initial. Final is the products, initial is the reactant, so enthalpy change is going to be H of the products minus H of reactants. So if that's less than 0, we just rearrange this and we see that the enthalpy of the reactants, we move this to the other side here, enthalpy of the reactants has to be less than that of the products. So anytime delta H is 0, the products have higher enthalpy, so sorry, I think I messed that up. Can't do math today or anything really. Alright, let's rewrite this. So we have H of the products minus reactants is less than 0. We move reactants over and we see that I think I said that wrong the first time. The enthalpy of the products are less than the enthalpy of the reactants. Okay, so anytime it's a negative number, products minus reactants, that means products have smaller enthalpy than reactants. So choices A through C distinguish those. So the products in this case are going to be the solution, aqueous barium hydroxide. The reactants are going to be the solid barium hydroxide plus the water that we're dissolving in. So again, this is our initial state. Solid barium hydroxide, our final products are the dissolved solution. So we want the one where the products is smaller than reactants. So this one says that the enthalpy of solid is less than that of the solution, so that's wrong. Choice B, the enthalpy of the solid plus water is greater. That looks like that's correct than that of the solution. So this one's our answer choice. Choice C says that they're the same. That would only be true if delta H was 0, so that we can get rid of. So of these three choices, one of them must be correct because the relative enthalpies of reactants and products must have some relationship, either products greater than reactants, less than reactants, or the same. So choice B is the one that works. Between D and E, we can verify that these are also false. The temperature of the solution is lower. So remember that whenever we have an exothermic process, delta H is less than 0, but that also means that the temperature of the surroundings will increase. Okay? So if we have an exothermic process, we would expect the temperature of the solution to be higher. So that one is wrong. This should be the temperature should increase during the exothermic process. And then here, the last one asks about work. So when barium hydroxide dissolves in water, the system does work on the surroundings. We can't really say anything intelligent about work here. Delta H just relates to Q, as we said earlier. We don't really know if the system is expanding or contracting or anything like that. And as we said, for processes involving solids and liquids, as we're doing here, the work is generally very, very small anyway. So this one, we don't have enough information really to even evaluate it, so that one's not going to be a correct statement either. Alright, so then all that's left is choice B is the only one that's correct, which is that the enthalpy of the starting point, the solid ionic compound plus water, must be greater than the solution if we're going to have an exothermic process. Okay, let's move on to the next one then. Sorry, I had to pause there for a second. Alright, and then this last one that we're going to have as a request from students, it again deals with just the comparison between delta H and delta E. And this time we don't even have to do it numerically, we just compare the two. So remember that delta H is equal to delta E plus P delta V. So if we're comparing delta H and delta E, we need to know, is P delta V going to be positive or negative? So P delta V, which is again the pressure times the change in volume, that's going to be positive if the moles of gas increases. Remember we said that gases take up more volume than liquids. So if you have more gases on the product side, your volume increases, P delta V will be positive. P delta V is going to be negative if moles of gas decreases. So if we're getting smaller, that means we're going to have a negative P delta V term. Remember, the P delta V is actually the negative of work, so there's a relationship there too. And then finally, P delta V is going to be 0 if there's no change in moles of gases. So all we do is look at each of these chemical reactions, figure out how many moles of gas are on each side. So for choice A, we have on the reactants, on the product side, we have 2 moles of gas. On the reactant side, we also have 2 moles. So on the product side, we have 2 HBr, that's 2 moles of gas. On the reactant side, we have 1 H2 plus 1 Br2, so we have 2 moles also on the reactant side. And so that means P delta V is going to be basically 0. Alright, so we wouldn't expect in this case delta H and delta E to be different. We're looking for the one where delta H is greater, which means we need to have a positive P delta V. That's what we're looking for. So this one is going to have a P delta V very close to 0, so we're going to eliminate that one. For choice B, we have one mole of gas on the product side, CO2 gas, and we have 0 on the reactant side. So in this one, we would expect P delta V to be greater than 0, which means that delta H should be greater than delta E. Okay? So we want delta H greater than delta E. That means this has to be non-zero, which means number of moles of gas increases, so that's going to be the correct one, choice B. If we go through the rest of these, in choice C, we have 1 mole of gas on the product side, 2 moles on the reactant side, 1 plus 1. And so 1 minus 2 is a negative number. That means we would expect P delta V to be negative, and delta H will be smaller than delta E. This one we don't have any gas at all, so we would expect, again, P delta V to be very close to 0 because we're not changing number of moles of gas. And similarly, choice E, it's all aqueous solutions and reactants. And as reactants, aqueous solution, liquid as a product. So Again, no gas involved, so we expect P delta V to be very close to 0. So these are, in this case, P delta V should be negative because we're decreasing the moles of gas. This one, P delta V, close to 0. This one, P delta V, also close to 0 because there's no gases involved. As we said, this one also, P delta V is equal to 0 because there's same number of moles of gas. The only one where the P delta V term is greater than 0 is choice B, and that's going to give us delta H greater than delta E. That's the one we're going to pick. Alright, then the last few that I'm going to go through now are going to be all problems that we had difficulty with, mostly numerical ones now, that I just identified from the Blackboard results. Now, a lot of these are numerical questions, and typically numerical questions do have worse outcomes, but there are going to be several different types that we'll go through here, and hopefully we'll see a lot of the different variations in these types of problems. So we have a few problems that we're going to go through that deal with heat transfer. So we have in this case we have 125 gram aluminum engine part, initially at 2.2 Celsius, and it absorbs 797 kilojoules. That should be heat. Sorry for the typo. It absorbs that much heat. What is the final temperature in degrees Celsius? We give you the heat capacity is 0.9 joules per gram Kelvin. All right. So for these problems, if we're dealing with heat, we know that there's only one equation that we have to talk about, which is Q is equal to mc delta T. And any of these terms could be the unknown. We could either be calculating Q, we could be calculating the mass, C, or delta T. So here what we have is we know the mass of substance, 125. We know the initial temperature. Remember that delta T is equal to the final minus the initial. So there's really going to be a difference of 2 temperatures. And we know Q here, which is 797, and we know C. So our unknown here is going to be the final temperature TF. This is a numerical question, by the way, so you probably had different numbers than these, but the process is the same. All right, so Q is equal to mc delta T, which is equal to mc times final minus initial temperature. And this here is going to be our unknown. We just have one unknown in this case. So 797 joules is our Q. That's going to be equal to the mass of the aluminum, which is 125 grams. The heat capacity of aluminum is 0.9. Remember, gram degrees Celsius or grams K are the same thing. And then we're going to do final minus initial. So temperature final is our unknown. Our initial temperature is 28.2 Celsius. Whenever we're dealing with a difference of temperatures, we can use Kelvin or Celsius because the difference between them will be the same. So we have some algebra to do here, so let me work it out real quick. So what we get is that 7.08 degrees Celsius is equal to final minus initial. So that means our final temperature is just 7.808 higher. And so what we get for our final temperature is 35.3 degrees Celsius. Okay? So we basically solve for delta T, which is this, and then that's equal to the final minus initial, so we just rearrange and get final temperature. In these problems, you can often at least check your work to some extent by just looking at the wording. So if the system is absorbing heat, anytime you absorb heat, your temperature has to increase. So your temperature that you solve for should be larger than the initial. If it wasn't, then you know that you messed up the math somewhere. But in this case, we do get a larger temperature, and that would be the correct value to correspond to 797 joules of heat. All right, I think I duplicated this one by accident, so that one we're done with. All right, the next problem here deals with heat and work. So we have change in internal energy. Change in internal energy is just sort of the lexicon of delta E. When we say delta E is change in energy, it means change in internal energy. It absorbs 109 kilojoules of heat. It has 56 kcals of work done on it. I think all the answers in this case were in kilojoules. This is multiple choice, but I didn't give all the choices. We want to know what's the change. So delta E is what we're looking for here. Remember that delta E is related to heat and work by just the sum of the two, Q plus W. So in this problem, they're both given to us, but they're in two different units, and we don't give you the signs directly. So it first tells us that the system absorbs 109 kilojoules of heat. So again, if it absorbs heat, 109 kilojoules. If it absorbs it, that has to be positive. Okay? And then W is going to be, we have 56 kcals of work done on it. So if work is done on the system, that means work is also positive. So you have to really read the problems closely to figure out if Q or W is going to be positive or negative. So if heat is absorbed, it's positive. If heat is released, it's negative. If work is done on the system, it's positive. If work is done by the system, it's negative. So again, reading the question carefully to figure out those clues to give us the signs of Q and W. Now the problem here that we're left with is that these are in two different units. I believe this one wanted it in kilojoules, even though it's not obvious from the wording that I have. So we have to convert kcals to kilojoules. So the work in kilojoules is going to be 56 kilocalories, and then it's 4.184 kilojoules per 1 kilocalorie. We gave the conversion as, yeah, exactly that. So we're going to just use that, and we multiply by 4.184 and get that our work is going to be 234 kilojoules. So then when we add the two together, we have 109 kilojoules for Q, which is a positive number, plus 234 kilojoules for W, which is also positive, and what we end up with is 343 kilojoules. Positive number. Okay? So that's delta E in this case. So if we give you Q and W, you just have to add the two together, but remember that before we add two numbers together, they have to be in the same units, and we also have to make sure that they're what their sign is, they're both positive in this case because it's absorbing heat and having work done on it. Those are both positive. Alright, this question deals with finding the unknown heat capacity of an alloy. So you have a 12.3 gram sample of an alloy, initially at 98 Celsius. We place it into 54.5 grams of water at 22 Celsius, and in an insulated coffee cup with a heat capacity of 9.2 joules per Kelvin. If the final temperature is 35 Celsius, what is the specific heat capacity of the alloy? So this is a little bit more involved than the ones we did in class, as I'll show you here in a second. So the concept is the same. We put a solid object into a calorimeter. So when we're measuring heat capacity, we put something in the calorimeter that doesn't dissolve in water. It's at a higher temperature into water that's at a lower temperature, and then the system equilibrates when the two temperatures are the same. So we have the heat for our alloy, the solid object that we're putting in this case, is equal to the negative of the heat for the calorimeter. Okay? And actually, we can write this either way. I think this makes a little bit more sense mathematically. Put the negative sign here, it just makes us deal with less negative numbers. But point of the matter is, we can put a negative sign on either side, but they're equal and opposite to each other. The heat for the alloy is equal and opposite to the heat for the calorimeter. So one side of this equation has to have a negative sign. And then writing these out then, heat for the alloy is just equal to mc delta T. So the mass of the alloy times its heat capacity times delta T with a negative sign in front of it is equal to, for the heat of the calorimeter, as we said, it's going to be mass of the water in the calorimeter, heat capacity of the water, times delta T for the calorimeter. Delta T's are not going to necessarily be the same, or they won't be the same actually. The one will be positive, one will be negative. Then we also have the heat capacity of the calorimeter itself times delta T. So we look at the information of the problem. We know the mass of the water in the calorimeter, so we have to include this term. We also know the coffee cup, which is the calorimeter in this case, has a heat capacity of 9.2 joules per Kelvin. So we also have this term, so we have to include both of them. So in this case, we have to include both the heat absorbed by the water and the heat absorbed by the calorimeter, which is this term, to be able to accurately do this. So now we can just start putting in the information we know. That remember that delta T is equal to T final minus T initial for both of these. So for the alloy, we have 12.3 grams. The heat capacity alloys are unknown. That's what we're solving for. So that's our unknown. And then the temperature change for the alloy, we have the final and initial. So the final temperature for the alloy is the same as the whole system. So the whole system ends up at 35 Celsius. So that's our final temperature. And then the initial temperature for the alloy is 98. So you have to make sure we put the right initial temperatures in on each side. So that's delta T for the alloy, and then that's going to be equal to the mass of water, which is 54.5 grams. The heat capacity of water is 4.184 joules per gram degrees Celsius. And then the temperature change for the water, same final temperature of 35. Remember that both things will get to the same final temperature, but the initial temperature of the water is 22, so use the correct one for that. Alright, and now it just becomes a bunch of algebra to solve for this heat capacity of the alloy. Alright, so let me work this out real quick, or as quick as I can, because you don't want to wait for me forever to do this. Let me pause this and do the math real quick. Alright, I left out a term here that I was in a hurry with. Make sure we include also the 9.2 joules per degree Celsius times the same delta T. Alright, so again, this whole thing here is the water. This whole thing here is the calorimeter. So I have to include both of those. Alright, so let me take a quick commercial break to do the math. Alright, so what I got then for solving for this unknown is 3.98 joules per gram degree Celsius. Alright, so as I said in this one, we have to make sure we include the terms for both the water and the heat capacity for the calorimeter. So these are the numbers for the water, 54.5 grams, heat capacity delta T. Same delta T, but a different heat capacity of 9.2 in this case for the calorimeter. Remember, there's no mass term in here because this is a total heat capacity of just joules per degree Celsius, no mass involved. Alright, so assuming I did my algebra correct, this is the heat capacity you would get for that alloy, 3.98 joules per gram degree Celsius. Okay. Alright, this problem here, we're talking about delta H for a reaction. This time we're going to calculate it, not using calorimetry, but using delta H as a formation. So we have a metal carbonate when heated according to the equation below. So this is our chemical equation. Delta H for reaction, knowing the delta H of formations for the reactants and products are given as these numbers. Alright, so in this case, if we have a chemical reaction, we're looking for delta H for the reaction, which is our unknown. Remember that if we're given delta H of formation for all reactants and products, the delta H for the reaction is just the sum of the delta H's of formation for the products multiplied by their coefficients, so that's what we abbreviate as M, and then minus the sum of all the coefficients times delta H of formation for reactants. Alright, so this is a lot like, mathematically a lot like what we did using bond energies earlier in the course, but this time it's products minus reactants, not reactants minus products. So delta H of reaction in this case is going to be, on the product side we have, this is already balanced, we just have 1 mole of MO times its delta H formation we have 1 mole of CO2 times its delta H of formation. So again, we're using the coefficients here. They're all 1 in this case, so it's all going to be 1 mole of each substance, but that could be something other than 1 if there's not coefficients that are different. So that's the product side, and then we're going to subtract from that the reactant side, which again is 1 mole of our metal carbonate times its delta H formation. Alright, so putting in the numbers then, what we have is 1 mole delta H formation for MO is the second number here, which is minus 525.7. One mole of CO2, its delta H formation is minus 393.5. And then we subtract from that the delta H formation of the reactant metal carbonate. So the metal carbonate has delta H formation of minus 655.2. So when we work this out numerically, we get two negative numbers added together. So again, don't forget the signs here. Okay. So we have two negative numbers, and then we're going to add together a negative, or sorry, subtract a negative number, which is the same as adding this number. So we get minus 264 kilojoules in this case. All right. So signs are really the only things that can mess us up here. We have to remember that for delta H of formation, if we're using that to find delta H for a reaction, it's products minus reactants, and we get minus 264 when we take these two numbers and add them, and then subtract this negative number here. All right. The next problem here then. That last one used delta H of formation, and if it's all delta H's of formation, we can just, as I said, we could just use this equation here, products minus reactants, don't have to write out all the equations. Now this one here though, we have delta H for this reaction here, given the information below. And these equations here are not all formation equations. This is a formation equation, but this one is not, this one is not. So we can't just use that equation, products minus reactants. We have to actually write things out and do Hess's law. So we have three equations down here, and the trick is to figure out how to combine these three equations to get this equation here that we're looking for, and then use the delta H's appropriately to find the delta H for that reaction. So if we look at the three, we have our equation that we're looking for has carbon as a reactant, and this first one also has carbon as a reactant. And that's the only place that we see carbon by itself in these three. So we're going to take the first equation and we're not going to modify it at all. Alright, so we're just going to take that exactly as written. I'll leave out the states of matter here. They don't really matter in this case. So we have carbon plus O2 going to CO2. This is the formation equation for CO2 as it turns out. And delta H for this is equal to just the unmodified first delta H, which is minus 393.5. Alright, now for the second one we have two sulfurs as a reactant in our equation, but on this one, number 2, we have one sulfur as a product. So we need to take this sulfur, we need to move it to the reactant side, and we need to double it. So we're going to, basically that's equivalent to multiplying it by minus 2. We're going to flip and double equation 2. Alright, so in doing so we get two sulfurs as a reactant, two oxygens as a reactant, and then we also get two SO2s. The delta H for this one is going to be minus 2 times the second delta H because we flipped and doubled this, so we're going to, flipping it makes the sign opposite, and then doubling it also doubles the delta H, and so that's going to be, let's see, 296.8 times minus 2 is minus 593.6 kilojoules. Alright, so that's the modified delta H for that one. And then finally, this last equation, we see that we have CS2 as a product. Equation 3 has CS2 as a reactant, so we're going to flip it. So if we flip equation 3, that's going to move CS2 to the product side, which is where we want it in our overall equation. So we flip equation 3, and we get CO2 plus 2SO2 going to CS2 plus 3 O2s. And the delta H for this, because we just flipped the equation 3, is just going to be the negative of that delta H for that reaction, which is going to be positive 1076.8 kilojoules. Alright, so we take this number and just make it positive. Now we can add the three equations together and make sure that they add up to give carbon plus 2 sulfur going to CS2. So on the reactant side we have carbon that carries through, O2 here plus 2 O2, that's a total of 3 O2s on the reactant side, but they're going to cancel with these 3 O2s on the product side. So again, anything that's on the reactants and product side cancels out, so we have O2 plus 2 O2s is 3 O2s, 3 O2s on the product, so that's all, those all cancel out. We have 2 sulfurs that don't cancel with anything. CO2 is a reactant, but it's going to cancel with this CO2 that's a product over here. And then we have 2 SO2s on the reactant side, but they're going to cancel with 2 SO2s on the product side from that equation. So everything else on the reactant side cancels out except for those two, and then on the product side all that's left is CS2. Alright, so this matches the equation that we wanted, and the delta H is just going to be the sum of these three. It's going to be the first delta H plus negative 2 times the second delta H plus the negative of the third delta H, which numerically is these three numbers. So it's going to be minus 393.5 kilojoules plus minus 593.6 kilojoules plus 1076.8 kilojoules. And I think this question was multiple choice, but the number you would have wanted to pick then is, I think, positive 89.7. Let me make sure that's right. Yes, positive 89.7. Alright, so with Hess's law, once we modify the equations and modify the delta H's, the last step is just to add those numbers together to get the overall delta H. Alright, so that was a pretty classic example of Hess's law. 3 more questions to go through, just variations on some things we've already talked about. Alright, so this one is another heat transfer problem. So we have 2 iron bolts, one at 100 degrees with a mass of 12.7, the other at 56 with a mass of 15.3, are placed in an insulated container. So assuming the heat capacity of the container is negligible, and what that sentence is telling us is that we only have heat transfer between the 2 pieces of iron, not to any other components in this experiment, what is the final Celsius temperature inside the container? So basically what we're doing is we're taking 2 pieces of metal, different masses, different temperatures, putting them together, and we should recognize that there's going to be heat transfer between the 2 until the temperatures are the same. So that means we have, if this is bolt number 1, and the other one, so that has this mass, and this one is bolt number 2 with this mass and temperature. We have to put a minus sign out in front of one of them, so the negative heat for one of them is going to be equal to the heat for the other, equal and opposite in sign. So equal in magnitude, opposite in sign, anytime we have heat transfer between 2 different objects. Alright, so this is the equation, and then for each of these we just have to write out MC delta T. So the first mass times its heat capacity times its change in temperature, which is going to be the same final temperature minus its initial temperature, is equal to the mass of the second piece of iron times its heat capacity and then its change in temperature. Same final temperature, which is what we're solving for, different initial temperature for the second one. Now here we gave you the heat capacity, which is 0.45, but in this situation, if it's just heat transfer between 2 objects that are the same material, C1 and C2 are the same heat capacity because it's both iron, and so these actually would divide out. We could put them in, we'd still get the same answer, but we don't actually need heat capacities in this case because it's the same material, so this term is the same on both sides. So now we just have to put in the masses and the temperatures to be able to solve for this. So the first one has a mass of 12.7, and then its final temperature is what we're solving for. We're solving for the final temperature of both, which will be the same. And the initial temperature for the first one is 100 degrees Celsius. And that's going to be equal to the mass of the second one, which is 15.3. And then its final temperature, which is the same as the other one, once they're done transferring heat, they'll have the same temperature, and its initial temperature, which is 56 degrees Celsius. Alright, I'm going to pause for just a second to do the algebra, and I'll come back with the answer. Alright, well, I didn't do it yet. I'm gonna just write everything. Let's distribute this. We have minus 12.7 grams times the final temperature plus 12,700 degrees Celsius is equal to 15.3 grams times the final temperature minus, when we distribute 15.3 times 56, minus 856.8 degrees Celsius. So again, we're solving for temperature final, so I will move things over. So we get 28 TF on one side is equal to 13,556.8 degrees Celsius. And when we divide these, what we get is the final temperature is equal to, I messed up something. Gosh, hang on. Alright, I know what I messed up. I was trying to do math in my head, and that's a bad idea in my case. So this should be 1270. So when we move everything over, we get numbers that are more reasonable now. And now when we solve for temperature final by dividing by 28, we get, we'll round it to 76.0. Okay? So that's what we get. Now, some of you might be sitting at home snickering and saying, oh, look at Professor Teese, he can't even do algebra, what an idiot, because I messed up this number here. Now, how did I know that I messed it up? So this is actually a good teaching point here. So the reason I knew that I messed it up is when I did the division and initially solved for TF using the wrong number here, I got a number that was bigger than both 56 and 100. Whenever you have heat transfer between two objects, one at a higher temperature, one at a lower temperature, the final temperature has to be in between the two. So if you don't get a number that's in between 56 and 100, you know that you messed up. So the first time I solved for this, I got some ridiculous number like 484 degrees Celsius or something because I had this number way too big. When I multiplied 12.7 by 100, I had one extra zero on there. So anyway, when I solved for TF, I got a number that was unreasonable. So I didn't show you all those things, but that's how I knew I messed up, and that's how I knew that I needed to sort of go back and rework this. All right, so I apologize for the mistake, but it ended up being a good teaching moment nonetheless. All right, last couple here are not ones that we necessarily had trouble with on the homework, but I didn't really cover this in class. I just want to make sure that we can follow the approach for doing this. So these are thermochemical equations. So we have a chemical equation and a delta H. And given this thermochemical equation, calculate the enthalpy change when 89.6 grams of SO2 is converted to SO3. So these types of problems we are going to treat exactly like stoichiometry. So even though this chapter doesn't really cover stoichiometry, this part of it is very much similar. All right, so what we're looking for is delta H. That's going to be what we're solving for, starting with 89.6 grams of SO2. And remember that this thermochemical equation tells us that when 1 mole of SO2 plus 1/2 mole of O2 is converted to 1 mole of SO3, those are the coefficients, 1 and 1, that means we have an enthalpy change of minus 99.1 kilojoules. So if we want to know the enthalpy change when we have 89.6 grams of SO2, we first have to convert this to moles, and then we can relate it to delta H using the thermochemical equation. So we're going to convert this to moles using its molar mass. So 1 mole of SO2 has a mass of, let's see, 32.07 plus 32, so 64.07. So that's the molar mass of SO2. We convert to moles, and then we're going to use this delta H, which is minus 99.1 kilojoules for every 1 mole of SO2. Now, it's 1 mole of SO2 because the coefficient is 1. If the coefficient was something other than 1, we'd have to put that number down here just like we do for stoichiometry. So this is a lot like stoichiometry, but instead of using mole ratios, we're using relationships between enthalpy changes and moles of substance from the coefficients. All right, so when we multiply this across, what we get is, let's see, we get minus 138 kilojoules. Or minus 139, I guess is probably the better way to round that, but both of those would have been fine. All right, minus 139 kilojoules when we multiply that out. All right, so that was relatively simple step one. And then in the last one we're going to do here, we're actually working backwards. All right, so here we're burning carbon, which is essentially the same thing as burning coal, as we talked about in class, to make CO2 with this delta H. If we want 693 kilojoules of heat, how much carbon must be consumed? So here we're going in some sense backwards. We're giving you the amount of heat that's needed. Remember that delta H being negative tells us that much heat is released. So if we need 693 kilojoules, that's going to be the heat that we're starting with. So we're looking for grams of carbon that we need to make 693 kilojoules of heat, to release 693 kilojoules. And so what we're going to do is just do a bunch of conversions. So 693 kilojoules, we know from the balanced equation that for every 1 mole of carbon, there's a coefficient of 1 there, we get 393 kilojoules. So 1 mole of carbon will give us 393 kilojoules, so we multiply by this conversion factor. So that kilojoules cancel out. Now we know how many moles of carbon we need. And then we just multiply by the atomic mass of carbon, 12.01, to figure out how many grams of carbon that corresponds to. So these work out a lot like stoichiometry problems, but we're just using the relationship between moles and kilojoules in this case. And like I said, don't be thrown off by the signs here. This delta H is negative, which tells us that heat is released. So we're just taking the absolute value of that here. You should never get a negative mass of substance, obviously. So if you got a negative number in this and you're calculating mass of substance, clearly you would just need to take off the negative sign to make that correct. So don't let the signs fool you too much. When we multiply this out, what we end up with is we need 21.2 grams of carbon to be able to produce 693 kilojoules of heat. Alright, so that takes us to the end of this one, a little bit longer than our typical homework review, but a lot of things to go over. So hopefully that's, things are more clear now. As always, more questions that you have, please come and find me or send me emails about them, and I'd be happy to address these or any other homework problems in additional detail. Alright, I'll see you guys in class later today, and hope you guys enjoyed this review video.